So first of all, I would like to thank the organizers for bringing me here all the way from Sweden. As you can guess by my name, I'm an Italian living in Sweden. I work in English. I understand a bit of Portuguese, but I cannot give a talk in Portuguese. So I will do my best to speak slow so that you can follow the translation in an easier way. What I will talk about today is a set of tools that we have available for studying evacuation in case of fire. And one important aspect that I want to underline is that my perspective is a bit different in a way from what you have heard so far, because I'm a pure academic. So as you can see, I'm pretty young. I am in the young generation of researchers in fire safety science. But I'm a specialist, so I've been working for now more than 10 years in this topic, in the topic of evacuation, especially with new technology, with new tools, with new methods to study evacuation. First of all, I will give an introduction on the group where I work, because nowadays, when we talk about research, it's never the work of one person, but it's always a collective effort. So there is a group, research group, with some colleagues, PhD students, master students, that we all work together in this area of evacuation. And one important aspect is that in Lund, the reason why I live and work in Lund, is that in Lund in Sweden we have one dedicated educational program on fire safety engineering. So the students, when they come from high school, they can go directly to fire safety engineering, which means that we have a group that is completely dedicated to do research in fire safety engineering and education. And within this group, we have different experts that work with different areas. So I am the one that work in the area of evacuation. So I will present first the expertise of the group where I work in. Then I will give some general concepts and some general understanding about understanding evacuation, because there is a lot of false myths or misconception about understanding evacuation, and we researchers have tried to categorize something that is very different to understand, which is human behavior. And following this, after mentioning some theories that we use to study human behavior as some of the experiments, both available from work from my colleagues as well as work that I've been doing myself, I will talk about some new technologies, new tools that we have to aid fire evacuation design. In particular, I will talk about two topics. The first topic is the use of computer simulations. Computer simulations are a very powerful tool for everything nowadays, but in particular, I will talk about the use of evacuation models, so computer simulations of human behavior, which is a very interesting and novel way of studying human behavior. And after that, I will push the bar in something even newer in the field of research where I work, and I will talk about the use of virtual reality. I don't know, maybe some of you have seen or have tried different type of video games that nowadays on the market, and you might try these goggles when you can have a virtual reality view. But what happened, a few researchers like me had an idea, if we can use virtual reality to simulate a virtual world, why we don't use it to simulate fires and study how the evacuation process happens during a simulated virtual fire. And this is a very new frontier of research. It's a very new field, but it has a very great potential, because when we do traditional evacuation drills in a building like this, we cannot really have a real fire in here. So we generally have simulated conditions. In a virtual reality world, we can actually have an exposure of people to a simulated fire as well, not just an evacuation, and then see what happens, how people behave. And with pushing the boundaries of the realism of the scenarios that we can create, we can also push the boundaries of our understanding of human behavior. And I will show you some examples of cases that we have studied both to help fire safety engineers, architects, and other stakeholders in the field to design buildings, but also to understand some of the fundamental parameters of human behavior. How did we do this? We reconstructed some of the very famous fire cases that are available and known in the world in virtual reality. And we had some people re-experiencing a fire evacuation emergency, and we were observing how they were behaving. It will probably be very interesting for you, knowing a bit of history of the fires in Brazil, to see that we also rebuilt one of the very famous nightclub fire, the Stardust fire in Ireland, which in a way can be compared to something that you have experienced yourself here in Brazil. And finally, I just want to launch some ideas, bring a fresh air of new technologies, a fresh air of new research that down the line can be used in daily design of buildings. And what you see here will not be just theoretical research that stays on the books of us researchers, but some of these concepts and some of these tools are already applied to design actual buildings, like the one where you are now. This is the evacuation group where I work, and we have a bit heterogeneous interests. My main interest is evacuation, and how you will hear today, I will talk about models, computer simulations, and virtual reality. My background is civil engineering and transportation engineering. And why? Because in the field of transportation engineering, it's very interesting to study optimization of flows of pedestrians, also in normal conditions. So when you design a metro station, a train station, an airport, you want to make sure that people do not wait too long in a line, or that the flows of pedestrians are optimized. So that's my background. And then I moved into the fire safety engineering business. I have a couple of colleagues that work also with the application of these concepts for risk analysis, and some they use also other type of new technologies. In Europe, it's becoming more and more common to apply building information modeling, which is a set of software that are used for representing a whole lifetime of a building. So not just the fire safety, but representing all parts of the lifetime of a building, from mechanical, from everything that has to do with energy balance, with energy efficiency of the buildings, and fire safety is a part of it. And then we have a pool of researchers and PhD students that work with us, and master students. So we are about 20 people every year that focus on this topic, that we do research exactly on this topic. So this is a smaller group within the larger group that we have that works with all topics of fire safety design in Lund. I will start with some theories to make you understand the type of research that we do. And this is somehow linked a lot to psychology and human behavior. What I will show you is one very classic experiment that is known in the literature of human behavior in fire. It is the so-called social influence experiment. So we routinely run experiments to study how people behave in case of a fire emergency. In these classic experiments from Latané and Darley, what they were looking is how people react when there is smoke coming in a room, when they are alone, versus how they react when they are in a group. So when they are alone, as you can see, a person reacts immediately and leaves immediately. So understand that there is a fire, understand that there is a smoke. This is all staged. It's an experiment. But once the same person is with some actors, because we have used actors in these experiments that do not do anything, even if they have smoke coming in the room, these actors that you see are basically trained to not act. And the person, even looking at the smoke coming in, do not react in the exact same situation. So in the exact same situation, the behavior of people can be very different in relation to the influence of the actions of other people. So you can see the time keeps going on, and the person looks around, looks at the people around. It's crazy because the room at some point gets completely filled with smoke. This is artificial smoke, of course. But you can see that the time keeps going on, and you will see that basically in a very similar condition, you have a completely different response. So this is just to show you the type of research that we do. What do we do? This is a classic experiment in the field of psychology. What do we do nowadays is we take some of the classic experiments available in the literature and we study them with much more technology that we have available today. So for instance, myself and some students, we repeated this experiment. And what did we use? We use eye tracking. So nowadays, you have some glasses that you can wear, and they track what you see, what you are looking at with your eyes. So if you are staring at an object instead of another one. So we repeated this classic experiment that you saw before available in the literature with actors and with an eye tracker. So people were just asked to be doing a fake task on a computer, and we will tell them, okay, we want to see how you reply to a questionnaire. And during the questionnaire, we have an alarm going off, and we see what do they do, what do they look at, how do they interact with these two actors that we have there. So if their behavior changes in relation to the actions of other people. So we try to understand the fundamental parameters that affect the decision-making of people when there is a fire evacuation scenario. Another theory that we use a lot in this field to explain some of the common misconceptions on human behavior in fire is the social identity theory. This is a very interesting concept that will make you understand why, in many situations, people behave altruistically rather than behave selfishly when there is an evacuation. The social identity theory, it tells us that if we are in a public space and we are with a group of people, like in this image, for instance, this is a group of people that is in a metro like you have here in Sao Paulo, like in any other place on the world, the presence of other people around you, you don't have any bond, any link with them. So it's just an aggregate of people. But when there is an emergency, when there is a fire emergency, automatically the people that you are surrounded with have something in common with you. And what do they have in common? They are all victims of the fire. So even if you don't have anything in common to begin with, you share an identity. And this is very important, understanding how can have an impact sharing an identity. There are some very interesting experiments done in the UK by some colleagues of mine to see how the impact of a shared identity affect the likelihood of people helping each other. For instance, and that's why I have this image here, they did some experiments, some social experiments, having people, actors, lying on the floor next to a stadium and having either a t-shirt of the team that was playing home, so it was Liverpool, Manchester, so they were in Liverpool. If they were putting a t-shirt of Manchester fan to a person on the floor, pretending to be sick and to not feel well, many people will just pass by and ignore that person. But if in the same situation, when the person on the floor will have the same t-shirt of the same team, of the home team, so the Liverpool team, a lot of people will stop by and ask, are you okay? How can I help you? What can I do for you? So it seems very easy to understand, for you, I guess, but this tells you a lot. This tells you that when we have a shared identity, a shared social identity, we are much more willing to help people around us. So when we have an emergency, we have a common misconception that everybody acts in a competitive way, in a selfish way. But with research studies of this kind, we can prove that in many instances, people are acting much more altruistically than we think of. So starting from these theories, we had to build a timeline. We had to build a structure of possible sequence of events that we could insert within computer models. Because nowadays, we have the opportunity to develop tools to aid the design of fire evacuation, and the tools that we use are based on computer simulations. So how do we implement the human factor, all these type of theories, in a computer model? We use timelines. So we have a behavioral timeline that tells us the sequence of the possible actions and reactions that people may have in case of an evacuation. So starting from the detection and alarm linked to a fire, starting from the ignition, then something happened that is different from the normal situation, and people have to start understanding what is happening, the so-called recognition phase. And after they have understood what is happening, in our case is a fire, they have to decide how to act to reduce the consequences. So a very important concept to understand, many researchers like me do not like the word panic. And why? Because the word panic seems to suggest that in all situations people act irrationally. Why? Because we see many cases people do not take the right decision in case of a fire. As researchers, what we say, we do not say necessarily, we don't use the word panic, but we say people do rational decisions in most cases, but not necessarily the correct ones. So taking a wrong decision or acting in the wrong way does not necessarily mean that people is acting irrationally, because when we talk about panic, we are referring about an irrational behavior, so a behavior which will lead negative consequences against ourselves. And if we look at the literature of big cases of great fires, we might observe behaviors that apparently they look irrational. Think about in the World Trade Center, people jumping out of the window. But in reality, when we analyze the facts, in many instances, we can find a rationality behind it. So we can understand that maybe that was a rational decision between dying trapped in a building or dying jumping out of a window. So in many instances, we do not have to oversimplify human behavior by saying, okay, this is just an irrational behavior, but we have to try to understand the reasons why certain behavior took place. And that's the job that us researchers in this field try to do. And after we do this, we can build models with sequence of actions and reactions that explain the possible behavior of people. We cannot do this with purely deterministic models, which means models that connect one action to one reaction. Because, for instance, if we have a fire alarm here, and if we have a fire alarm tomorrow, the type of reaction that you might have, even with the very same people, might be very different. But we can have a probabilistic model which studies in a probabilistic way how are the chances that a group of people will act in a given way. And that's what we do as researchers. We build probabilistic models of human behavior. So how these computers models work? We have tools that try to represent in a probabilistic way the human behavior, the human factor, and the movement of people in case of emergencies. And what do? We look mostly at two different factors. We look at the more physical factor linked to movement, so how people move when there is an emergency. So how many people can fit that door that we see in the back? How many people can pass through a given corridor? So this is the movement-related variables that we can study in very controlled laboratory experiments, and we do many of those. But we also have to study behaviors. So we have to study the human factor. And to do this, we use, as I mentioned before, timeline models, which is an abstraction of the sequence of actions that people do. And we try to represent decision-making. So what are the reasons why people take certain decisions? And why people in a very same situation might take different decisions? Because this is very interesting for us. So while for this movement aspect, we have now very sophisticated and I will say reliable models. So mathematical models or computer models to simulate the movement. Here I just mentioned a few, but many, they make an analogy between particles of a fluid, so like have a hydraulic flow, and how people move. So if you see people from the top, a crowd moving, you might make an analogy with the hydraulic flow. And we do this mathematically also. That's what we do. And these are other models that use similar analogies. But what we have problem with studying with mathematical models, pure mathematical models, is to study the behaviors. And there, instead, we don't rely only on classical mathematical models inspired by fluid dynamics or other fields of science, but we use the so-called agent-based models. Agent-based models are models that give the possibility to represent rules of interaction. So the so-called, in computer science, they call them if-then conditions. So if this happens, then something F will happen. And this gives us the possibility to represent very complex behavior and understand how these behaviors can have an impact on the evacuation. So what are the factors that we take into account in our evacuation models? We can represent the key aspects of the timeline that I showed before. So everything that happened before we decide to move towards a safe place. Everything that has to do with the movement, so the physical aspect of us moving towards an exit. Everything that has to do with the choice of the path that we want to take when we choose a way out of a building, and the constraints that we have in the space, because we might have obstacles, we might have other people around us, so our flow, our movement together has some physical obstacles that we have to represent. And how we put this together is with some fundamental relationship. So we conduct experiments in control scenarios in which we measure the speed of people, we measure the flow of people, so how many people can pass through a given corridor or a given door in a given space, and the density, so how easy it is for me to move in relation to how many people I have around me. So nowadays, researchers like me, like Professor Rosaria, we have several experiments that tell us how this mechanism works. And how do we use this? In Europe, it's getting more and more popular to use the so-called performance-based design code, which is a bit different from what you have here in Brazil. Here in Brazil, you use the traditional prescriptive-based design approach, which means that you have rules. You have a rule that tells you, for instance, that door in the back has to be at least, I don't know, X meter wide. The distance between the furthest point in the building and the door should be maximum, I don't know, 30 meters, 20 meters, whatever you have in your code. What we start using and we start seeing more and more popular is performance-based design that tells us, regardless of the configuration of the building that you have, I have to be able, as designer, to prove that that building is safe. And how do we do this? We use models to calculate the time that it takes to leave a building, and we compare it to models that calculate the time until the conditions in the building are not safe anymore. So we can use models for fire simulation to understand, okay, I have 2 minutes or 3 minutes before I will get intoxicated in this building, and I compare this with the time that it takes for everybody to get out of a building. So this is what we use, and that's also what we teach in Sweden. There is one more problem, though, that when we deal with fire, we don't deal only with the movement of people in a condition like this, like with lighting, clear conditions, but we might have situations in which we have smoke. Especially, we were talking before about underground spaces. Think about a tunnel, for instance, in which there is no compartmentation. So the smoke, at some point, will enter, we get in contact with people. So what we do is to conduct research on studying the movement of people in low visibility conditions. So in Sweden, what we have been doing, we had a couple of projects with the Ministry of Transport in Sweden that tells us, okay, we have to design a tunnel, but if there is a fire, we know that people will most likely enter in contact with smoke. So how long will it take them to get out of a tunnel where there is a fire? and what is the decrease in walking speed that they have due to the visibility conditions that are reduced. So what did we do? We did experiments in which we closed down a tunnel, we put artificial smoke in, we had thermal cameras, and we started filming how people move around in a very low visibility condition. So as you can see here in this video, this is basically a firefighter following one of the person that was doing our experiments. And you can see that the person completely changed the way of moving, because when you are in low visibility condition, you start using your hands to help your movement, and you a lot rely on the emergency lighting as well. These lights that you see every once in a while. You see, this is an emergency light, so people look at this emergency light to find the exit. And then what did we do? We started changing the configuration of the emergency exit to try to attract people to them so that it was easier to find their way. So we used different type of flashing lights, we used different type of sounds to see what was the optimal design for people finding their way out of the building, in the tunnel in that case. And from this, we can also build some relationship between the walking speed of people and the visibility conditions that we express in terms of extinction coefficient. Often we use light extinction coefficient instead of visibility. It means the same thing, but light extinction coefficient does not depend on the object that you are observing. So in the same room, if we have the same smoke, if we have an object that emits lights or that reflects light, it's much different the situation that we will experience. So that's why we build this relationship with this parameter. So as I was mentioning before, we are trying to transition from the very, unfortunately, commonly used panic word, which we see a lot also in codes, also sometimes even some researchers that are not from our field, they use these words. And I understand why they use it, because traditionally in what we always think when we think about a fire evacuation emergency, we think about irrational behaviors. But the reality is different. The reality is that it's a simplified way to look at things. Instead, we should try to understand in reality what happened and what are the decisions and the process of taking decisions that led to a given behavior. But how do we do this with models? It's very difficult to account for the human factor. I always use this quote from Newton. Newton said, I can calculate the motion of heavenly bodies. You know, he was a very famous scientist, but I have problem in understanding the madness of people. So how do we do this? What do? We do not use models and mathematical models that give us one result for one input. This is not the way we do it, because in most cases, if we do it in this way, we will be wrong. We have models that are probabilistic. So they say, given the condition, given the room, given the likelihood of a given population, there is a range of possible behaviors that might be observed. And then we analyze probabilistically these results. So what we do, there are some mathematical methods. I've been a lot involved in developing this type of mathematical methods to treat results of probabilistic models, to study average behavior, very common behavior, probabilities of having a given behavior, and see how the results of a given model converge towards an average scenario that we can expect with a higher likelihood to happen. Very often we have this misconception that we have to reach the risk equals zero. Unfortunately, the risk equals zero does not exist, but we have to build in a way that we are confident that the risk that we achieve is extremely low. And that's the challenge that we have to achieve. So to do this, we have these models that can tell us, okay, the likelihood of a given behavior is very high, so how am I gonna deal with it? And how am I gonna tackle this problem? And as I said, this is something that now we can study with some mathematical models. But the question that I often receive is, okay, you have some computer models, but how are they valid? How can I use those computer models in the real world? They are just a simulation. So what we did a couple of years ago is to try to build a document. This was, at the time, I was working not in Sweden. For some time, I've been working at NIST, that is a research agency of the US government. And there, together with Lund University, where I work now, we try to make an effort to categorize and list a set of tests that these models have to pass in order to be able to say these models are actually predicting human behavior. So if you're curious to see how these models work, I strongly recommend you to have a look at this document. It is freely available, and you can just put it on Google, and you will have a better idea on how the models can be validated. But okay, the models can represent behaviors. The models can model the movement of people. But where do we get the data to calibrate these models? So this is a big question that many people in the field has. And there are many ways of doing this. We can use hypothetical studies, which means questionnaires, that, as you can imagine, they're not really reliable, because if you just ask somebody, what would you do if you are in that situation, you don't really feel how you will be in that situation. We can use case studies. So look at the picture of the World Trade Center. This is very good and valid data because we can really understand what happened in reality. But fortunately, they are not so common, so we don't have the opportunity to have so much data to study different conditions. And in many cases, the condition that we might face in a new fire might be different from the previous one. So what do? We arrange, as I showed you before, field studies and drills, but also lab studies. So studies in the laboratory in which we control all the conditions of the fire evacuation that people experience, and we study what people do and how they react. And I will talk to you more about one method for doing lab studies, which I think is the future of our field. And this is virtual reality. I don't know if any of you, how many of you have tried virtual reality before? The goggles, can you raise your hand? There is a few people. So we start from a real environment, which is where we are now. We have augmented reality when we add something on a real environment. We have augmented virtuality when we have a simulated environment, but we interact with physical object within it. A classic example, I had a student that built simulated fire scenarios, but he rigged an actual fire extinguisher to see how people will extinguish with a real fire extinguisher a fire that was in virtual reality. This is augmented virtuality. And the virtual environment is a simulated space. So what do is we use virtual reality because we have the possibility there to immerse people in a simulated world and have them feeling to be there. And nowadays, the level of realism that you can achieve with this is extremely high. So what do? We have the so-called feeling of telepresence. So even if you're sitting in this room, if you put some visors or some goggles with virtual reality, you might feel that you are somewhere else. And in our case, this is very useful because we can have people feeling that they are experiencing a fire evacuation scenario. So how does it work? We start by building a 3D model of a building that we are interested in with one 3D modeling tool. Then we import it in a video game engines because there is a lot of research done in this in the video game industry. And this industry nowadays, it's even bigger than the Hollywood business. So now it overtook completely the movie business. The money that they have in there, it's crazy. But what is good for us is that there is a lot of technology available for us researchers that we can use. So what do? We build a scenario, we import it in a video game engine, which is a software to develop video game, and we create a story. We create a fire evacuation. We create a set of events. And what we can do with virtual reality, we have very good opportunity to have experimental control, so to manipulate completely the scenario that we had. We want to have a fire in a room, in another room, a given emergency sign, a given situation. We can change everything. And as you can see in this table, the VR experiments compared with other methodologies to study human behavior in fire is scores quite high because when we see at the validity and the different validity that goes from the studying the links between cause and effect in a given context for internal validity, or the relationship between real world and the phenomena that we are observing, that is the ecological validity, or the generalization of the findings that we find, which is the external validity, VR scores very high. So it's a very good tool for us to study this. So what do we have in Lund? In Lund we have a lab in which we have a room, which is basically 4 meters by 4 meters, in which we could have people experiencing a fire evacuation scenario. In some cases, we have done experiments with scale 1:1. So imagine, for instance, that you are stuck in a hotel room where there is a fire. So we did this experiment with a scale 1:1 in a virtual environment. And we also used the goggles, some of the commercial goggles that you have in the video game industry, like Oculus Rift or HTC Vive. And what we also recently bought is an omnidirectional treadmill. An omnidirectional treadmill, as you see, is like the one that the babies have when they have little, so you can actually move around. So you have an harness, and you actually move, but you stand still. So this gives us the opportunity also to study the movement of people, so even higher level of realism. And now I have a question for you, because I want to see how much experience you have with virtual reality. As I said, the level of realism now is getting better and better. So I want to hear from you who thinks that among these three thinkers, which one is the real one and which one is the computer-generated one. So who think that the first one is real? Please raise your hand. Who thinks that the second one is real? Who thinks the third one is real? I can tell you that you are all wrong, because they are all computer-generated. So you can understand that the level of real, you cannot distinguish nowadays. You cannot really distinguish nowadays. So what I want to say is that the level of realism is getting better and better. But when we build this fire evacuation scenario, sometimes we have very complex buildings. For instance, we did a project recently for CERN, which is a particle accelerator tunnel. And they wanted to study how was the evacuation in their particle accelerators. And this is a very complex scenario. So what we did is we had to reproduce the scenario, keeping it at a fair level of representation, but without having too many things in there that might distract the person from our task. Our task was to study the human behavior in case of emergency. So there is a trade-off between how much we can push the limits of realism and what is also feasible to do. So what we do nowadays with VR, for instance, we can compare different fire evacuation solutions. So for CERN, they are now having a very large project for an infrastructure of tunnels 400 meters below ground, and it's not built yet. So they could not do any evacuation drill. They could not do any test. And they asked us, could you build this in VR, and we can test which solutions can work. And one very interesting thing is that in this type of facilities, they use robots on the ceiling for maintenance. So for basically having maintenance of the tunnel accelerators and the accelerator that they have within the tunnel. So we said, how will people trust information if they get it from a robot and not from a human? Now you can imagine this type of experiments will be extremely expensive to do in real life, because we talk with the robotics group in CERN. These kind of robots are very expensive, and to build them and to rig them, we don't have a facility where we could install it, so it will be extremely expensive. So they asked us, could you build this in virtual reality? And then we will study what happened. And what we did then, we compared different solutions, and we saw which one was the one that people will follow more. So if we will use a robot, if we will use dynamic signage, so sometimes you have on the walls of a building some information given there, or information given on the floor. So in this way, we could study even very complex systems that possibly are not even built yet, or they do not exist. So real prototyping with very low cost. And we did something similar also for tunnels that are in road tunnels, so classic road tunnels. And for instance, one question that we often have is, how do we design the emergency exit portals? Which colors should we use? Should we use green, white, blue? If we use flashing lights, what frequency should they have? And how the portal should look like. Also in this case, we did experiments in VR to study this type of scenarios. And again, this is for us building a video game, and then we have people, we tell them, okay, we want you to test a video game. We don't tell them that there is a fire scenario. And then we launch the fire scenario during the actual virtual reality scene, and we see how people react. So what do they do? How do they act? What are the decisions? But also here, we start getting a lot of questions. Okay, you are doing this very realistic, sophisticated fire scenarios in virtual reality, but these are not real because people do not feel to be scared for their life, to be afraid for their life. So what do we say? We need to validate this approach. How do we do it? We take some actual cases from real fires that happened and occurred in real life, and we put them in VR. We put them in a virtual reality scene, and we see how people behave in these type of scenarios. And then we compare the behavior in the virtual world with the one that we have from the fire investigation report, so the actual behavior in real life. And we did this for different scenarios. We did this, for instance, for scenarios where people are alone, and this is the one that I was mentioning before. So basically, when you are in a hotel room and there is a fire coming out, with some smoke coming out from a smoke vent, and you are stuck in your room, or when you are in a crowd. So this is the case that I was mentioning at the beginning. So we even studied how people interact in a fire evacuation scenario in a disco. And this was reproducing the Stardust nightclub fire, which is a very famous and known case in the literature. This case instead was the NGM Grand Fire in Vegas. You probably, if you work in the fire safety business, you have heard of these cases. So with this type of experiments, we can then validate our method and even potentially what we want to do to bring this method for forensic use. So rather than having just survivors' interviews and information from the rescue service, we would like to have people re-experiencing, retesting a virtual scene how it was in reality. And from there, we can also study what would happen if. So what would happen if the action of the crew would have been different? If a given system would have worked or would have not worked? If the alarm would have gone off earlier? So this is a tool that we want to bring forward for forensic applications as well. And this is just a video that I want to show you, final video, on how a VR scene looks like. So basically, you are immersed in a virtual scene, and you start seeing smoke, for instance, coming from the vent, and you have the freedom to go around, interact with objects. This was 1-to-1 scale, so people were in a physical room which had the actual size of the room in which the fire was occurring. So what we study is how long does it take for people to try to find their way out? What do they do? Can we reproduce very complex behaviors? And in this very experiment, we even managed to see extremely complex behavior. Imagine, without telling to people that there was even a fire, we started seeing people taking the pillows from the bed, going to the sink in the toilet, wetting it, and going to the smoke vent that you see before to try to block it. So even behavior which are not very simple can be reproduced in VR. So this gives us a lot of hope for future research because we can understand more and more about how human behavior function in case of fire evacuation. So to conclude, I wanted with this talk to give you information about the new tools that we have today available for studying human behavior in fire and the research that we do in Lund and that some of the colleagues do around the world. Professor Rosario is one of the very known professors around the world that works with this as well. So what I showed you is the great potential that we have with evacuation models that can really help the design of buildings, because we really can test and understand what will happen. So in that case, we will not just follow a prescriptive rule that tells us, okay, if I put an exit of 2 meters, this building is safe. No, I will even test if that side of an exit is appropriate or not. And finally, I talked about VR, virtual reality, which I think is the future for our research field, because it gives us really a list of possibilities that we didn't have until now, because we didn't have this type of realistic scenarios. We could not build so much realism in the virtual world. So I thank you with this, and if you have any questions, you're welcome to ask me afterwards. Thanks.